Well, good morning.
Good morning.
How are y'all doing today?
Excited to get the week started, you know?
Yeah, me too. Oh, looks like we got a problem on Zoom again.
Say you love me.
Sorry, Matt. Something's gone wrong with your Zoom.
Just give me
And
something.
you're logged in about
so
50 times.
move on. Pull me closer or push me away. Let me know if we'll be okay. 'Cause I can't stand another moment of you playing with my mind. I'm so tired of never knowing, so spell it out.
There. That'll take care of it.
Stay awake till morning. I won't stay another night. If you're feeling something for me, say it now.
All right.
'Cause I can't wait for you.
So we've reached a point in this semester where we've basically done all the material that we were going to do in the curriculum, do on the syllabus, and so we're just into the extra stuff. So we've got this week and we've got next week. Now next week, for most of you, is finals week. So I know you're busy doing all of your, wrapping up all your assignments for your other classes, but for this class, there is just a couple more things to do. The first one is, and I haven't got this posted yet, but there is going to be a self-assessment that I would like you to do. It'll show up in Canvas here in the next day or so, and it just basically as you go through your entire course and reflect upon the learning you did and the work that you did, and just summarize all that in one place. So look for that in the next day or so. You'll get an announcement probably when that's posted and live. And then the second thing to do that you'll need to do next week is meet with me for about 5 minutes or so, just to go over that self-assessment and try to arrive at a consensus about what grade you're going to get in the course. So those two things need to be done over the next 2 weeks. So again, in the next day or so, you should see a entry show up in the sidebar on Canvas that says Confer Zoom, and that'll take you to a calendar. Look for the calendar for next week. That's December 5th through the 10th. And find a time slot that works for you and sign up for one of those time slots. And then during that time slot, again, the meeting will only take about 5 minutes or so. You'll meet with me and we'll go over your self-assessment, we'll go over your assignments, and we will see what grade you're going to get in the class. The other thing to do is between now and next week is go back and work on any assignments that have not been completed. Remember, you can turn in assignments late. Just please try not to do it all at the very last minute, otherwise I won't necessarily get to it before we do our meeting. You may want to do your meetings early in the week and get them over with rather than doing them later in the week and then possibly find out there's more stuff that you could have done. So maybe try to get it done a little bit sooner than later. Are there any questions about that process?
Sounds good.
Okay. So as far as today's material, I had mentioned a couple of things that we could do. I'd mentioned million more machines, and I'd mentioned quantum computing, and I think I decided to do quantum computing today. Well, actually, no, I did decide to do quantum computing today because that's what I planned to do. I read a little bit about it over the weekend, and also I think it's going to be a nice tie-in with my other class, my C programming class that meets on Tuesdays and Thursdays. Again, we're also approaching this kind of like optional week or so. Actually, we may do the quantum computing in the C programming class next week, or maybe we'll do it. Maybe we'll do it on Thursday. And that's where we'll actually run like a little simulator we'll write a C program that simulates a quantum computer. But today, I think we'll just get like kind of an overview of quantum computing and what it means and what it can do and what it can't do, and learn a little bit about the mathematics behind it. Just a little caveat here, I only know about this much about it, right? I took one of those online courses on Introduction to Quantum Computing last year, and I learned a lot, but it's just the tip of the iceberg about what quantum computing can do. So I'm just sharing with you what I know about it, which is really not that much. So I've got like this video for you to watch first, and let me get that set up. It's not a really great introduction to quantum computing, but it is kind of an introduction to it. I forgot to get this set up ahead of time, so let me go ahead and get that going. And I got to get through the ad first on YouTube. Okay, so hopefully this will all work when I bring it up. Oh, let me do this here first. So that people watching on Zoom, this won't be so jittery. Hey, that's cool stuff, huh? Any comments about that? Yeah, no, that's pretty cool stuff. I mean, I'm looking at the chat here. She did a good job presenting, yeah. I mean, like, it's not really an introduction to quantum computing and how it works. That's what we can talk about over the next hour or so. YouTube says the stream has been temporarily blocked because we detected a copyrighted audio stream. Well, hopefully it'll come back online. That's because I played a YouTube video on my YouTube stream. So, we'll see if it comes back. Sorry about that, YouTube people. We'll have to figure out some other way of doing that later. That's the problem with YouTube, is you can't like to show YouTube stuff on YouTube. I wonder if you guys can hear me. Let me quickly post something on that chat. Okay, looks like they'll be back pretty soon. So, here's what I know about quantum computing. So in a classical computer, you've got a classical bit. We just call it a bit, right? It's a 0 or it's a 1. It's never both, and it's never neither. It's always either a 0 or a 1. But a quantum bit, which is just called a qubit, uses a particle with quantum properties. It could be something like a photon, or an electron, or an atom with energy states. Here's this kind of simplistic view of an atom. You've got the nucleus in the middle with its protons and neutrons, and then you've got electrons orbiting around the nucleus. And those electrons could be in a low energy state, in which case they're kind of in an inner orbit, or they could be in a higher energy state, and they move to an outer orbit because it takes more energy to move it around the nucleus in that case. So maybe you could use something like the inner orbit is a 0 and the outer orbit is a 1, or something like that. But the thing about quantum particles is that, and this is kind of weird, is that the electron does not, when it moves from one state to the other, it does not like gracefully come from the outer to the inner one the way a satellite would, to go from a lower orbit to a higher orbit. It actually just, it jumps between those two orbits. At one moment you could be looking at it and it's in the inner orbit, and the next moment it's in the outer orbit, and it never traversed the space in between them. So quantum particles like these electrons can exist in what's called a superposition, which means that we don't know whether they are in the inner or the outer orbit. They could be in one or the other, we don't know. But when we actually measure it, when we actually measure the state of that electron, it then suddenly snaps into one or the other. Until we measure it, we don't know. But at the moment we do measure it, we do know the answer. And so electrons and quantum particles are said to exist in a wave state, and then when we observe the state of the wave, it collapses down into one or the other. So the presenter said something like, we don't exist in this quantum realm, and that's true, right? We don't see things being in either one or the other, but you can kind of get a feel for that if you were to like flip a coin. While that coin is spinning, you don't know whether it's going to come up heads or tails. And in fact, when it lands on your hand and you slap your hand over it, you still don't know whether it's a heads or a tail. But then when you look at it, suddenly it's one or the other. That's not really actually a quantum effect, but it's kind of like the same idea, is that until you actually look at the coin, you don't know what state it's in. The problem with that is that we do know it's in one or the other. We know it's definitely in one or the other. It's never going to be like on its side, because you'd be able to feel that. But while it's spinning and while you've got it covered up, you just kind of like don't know what it's going to be. So this is the game that she said her quantum computer played. First of all, a classical bit is represented as a 0 or a 1. Qubits are represented using a different notation, a slightly different notation. We've got this vertical bar and then either a 0 or 1 and then this little arrow. And that represents a single qubit. So what her computer was doing was it would start out with the qubit in a 0 state, and that we'll say that 0 is heads and 1 is tails. And then that mixing operation that she talked about is represented using the letter H. H stands for Hadamard. I think it's 2 M's. Maybe it's 2 D's. That doesn't look right. And then X, the operation in the middle, which is where you got to flip the coin either to the other state or leave it. We'll call that the NOT operation. Okay, so you take this quantum bit, you start it out in the 0 state, and then you mix it up, you put it into a superposition, so you don't know whether it's heads or tails. And then you can optionally flip it one more time, and then you do the superposition thing again, and it pops out being heads. That's kind of strange, right? So it's almost like we took a coin, which we know is in heads, we flipped it so it's rotating in the air. We decide whether to let it go one more flip or to stop it. And then it's almost like we flip it again, and then it lands up heads every single time, no matter whether it flipped over 100 times or 50 times, or 20 times, or 21 times, we flip it again, and then it always lands always lands heads. So that's kind of strange, but we can show that that's how the quantum computer works. So first, a little bit of background. Scientists didn't realize that this quantum universe exists below our field of view, essentially, until they did something called the famous two-slit experiment. And it starts like this. And you can actually do this experiment at home. All you need is a laser pointer, and you don't have to use a fancy one like this. You can just go to the dollar store and get a cheap $1 laser pointer. And then you need some kind of something really thin that you can cut two little slits into very close together, like less than a millimeter apart. So you can use like a piece of aluminum foil, or some people, what they do is they get a little piece of glass and they hold it above a candle so that soot coats the glass and makes it black, and then you use a razor blade and you cut two little slits into the soot. Or you could even use something like a pet flea comb that has the tines really close together. So all those things will work pretty well. And in this experiment, they took the laser and first of all, they shined it through one of these screens that only had one slit in it. And you get the effect that you expect, which is, let me erase this, and we'll draw this screen here with a single slit in it. You get the effect you see, which is all the laser is kind of like focused onto one single point on a viewing screen beyond the slits. And it's almost like taking a gun and shooting bullets through a little tiny hole, right? The bullet holes end up on the wall opposite in a condensed single pattern. That's exactly what you would expect. And so physicists at that point said, well, light behaves like a particle because you shine it through a little aperture and then they appear as one single spot on the wall. But then they put two slits into there, and they got a completely different effect. So rather than getting two spots on the wall, which you would expect if you were shooting bullets through two holes, right? If you shot bullets at a screen that had two apertures in it, and you kind of just randomly shot around, you'd expect the bullets to end up in kind of like two concentrated spots on the opposite wall, which is exactly what would happen. But when they did it with a light, with laser, they got a completely different effect. Sure enough, they got a concentration in the middle, but then they also got these smaller bands of light spreading outward from it. And they've seen this before. They've seen it before when they take like two pebbles and they drop into a pond and it creates ripple patterns going out. Where those ripple patterns intersect, you get this same pattern. It's called an interference pattern. So where the troughs and the peaks of the ripples on the lake collide together, they amplify each other when the peaks come together and when the troughs go together, and they cancel each other when a trough hits a peak, and they cancel out and they make it flat. So they said, well, this is kind of strange, right? When you shine light through these two slits, you don't get two spots. You get a whole bunch of spots spread out, and it looks just like the pattern you get when you have these two ripples appearing in a lake and they intersect with each other. And so that led physicists, scientists to realize that there was something different about light. And they said, well, what else can we do with this? Like, so that probably means that light is actually a wave. And at the time they were doing this, about 100 years ago, they really didn't know actually what light was. They didn't know whether photons, they called them photons, were little tiny, almost like little ball bearings or little BBs, little bullets, or were they actually something else? And so they theorized, they hypothesized that they were, almost like little balls. And then they did this experiment to see what would happen, and they realized that they were wrong. That light does not behave like little balls, it behaves like waves. So they said, well, maybe light is actually waves. Let's see if we can test that. What we think is that light acts like waves, and so one of the things they did was they replaced this laser. Oops, I didn't want to erase that. They replaced this laser with a device that could shoot out photons at a very slow rate. Right, so they said, well, the problem what might be happening here is that we don't really know if light is a wave or not. But maybe what's happening is there are so many photons finding their way over to the slits that some of them go through the left-hand slit and some of them go through the right-hand slit. And because they're packed so close together, they're actually influencing each other. Right? As one of them passes through a slit, it causes another one that's really close by to maybe go through the other slit, right? Maybe they're hitting each other or something like that. So what we're going to do is we're going to slow the photons down so that only one of them can be in transit at any given time. And that way there's no way at all for those photons to interfere with each other. It's almost like, rather than using a machine gun that shoots out a whole bunch of bullets all at once, we're going to use a pistol that shoots only one at a time. And we're going to see what happens. So they slowed this down. And this is where you can't do this at home because it costs, many hundreds of thousands of dollars to get a special laser pointer that only shoots one photon at a time. But it can be constructed. It can be done. Basically, you take the same idea of a laser, but you cool it way down so that it operates very, very slowly at that point when it's very, very cold. So you got this slow laser that's shooting just one photon at a time, so far apart that there's no way they could interfere with each other. You pass it through this double slit, and it'll take some time to build up what you see on the screen on the opposite wall, but you start getting a whole bunch of dots. They start scattering around, and it so happens that you get the same interference pattern building up over time. And the scientist said, that's really weird, right? Now there's no way for those photons to interfere with each other, but we still get the interference pattern. And the only way that could happen is if that one photon, was simultaneously passing through both slits and interfering with itself and causing it to either go this way or that way or go straight across. The only way that could happen is if the photon is not a particle, if it's actually a wave. And it doesn't become a particle until it hits the screen on the opposite wall. Okay? So you slow the photons way down so they can't interfere with each other, but it acts like it's interfering with itself. That photon is going through both slits, almost like you're dropping, instead of dropping one rock on the water, that rock somehow splits itself into two rocks, and they drop next to each other, and they create that interference pattern on the lake. Very weird, right? And so they said, well, let's test this out for sure. Since we've slowed the photons way down to the point where they're only going one at a time, what we're going to do is we're going to put a detector next to one of the slits so that we know which one it went through. In fact, we could put detectors next to both slits and see whether they're appearing at the same time through both slits, or if they're only appearing on the left one or the right one. So we'll put these detectors up, and we'll see which slits they went through. Okay, so got this other picture over here. Got these photons going through. And this time I'm going to show like an overhead view. And there's a detector here that's looking this way. And there's a detector over here that's looking that way. And we've got our double slits. So let me, I'll draw it like this here. Okay. And then what do you think happened? What did they see? Well, what you see is the interference pattern goes away, and you get just two spots on the screen. The scientist said, whoa, wait a second here. All right, all we did between this experiment and this experiment was we put these detectors up to detect which slit it went through. That's all we did. We didn't change the slits. We didn't change the wall that is going on. All we did is we put up these little detectors. And the photons don't even touch the detectors. They just pass by. And we just see if they went past. That's all we changed, and the interference pattern went away. And so they said, well, okay, well, maybe it's the presence of the detectors. Maybe somehow the physical presence of the detectors is causing those electrons to now go through one slit or the other, but not both. So what we'll do is we'll just turn off the detectors. Right? We'll leave them up. They're still there. We'll just turn them off. And the interference pattern comes back. All right? So the physical experiment is set up the same way. You turn the detectors on. You don't tell the photons that you did that. And the interference pattern goes away. You turn the detectors off. And the interference pattern comes back. It's like the photons know if they're being watched. If they're being watched, they act like particles. If they're not being watched, they act like waves. That's crazy. And so that led to this idea that photons, and in fact all quantum particles, can be either waves or particles, depending upon whether they're being watched or not. That's crazy, isn't it? And they've even done other experiments. I mean, many experiments to like show that this is in fact true. They've done another one where they have this laser, right? And you've got this beam of light coming out. And then you got your double slit over here. And then, you get your waves coming out and they interfere and you got your interference pattern. But then they stick a, what's called a half mirror here. Half mirror means that half of the photons will go through the mirror and half will get reflected off the mirror. So this beam gets split. And it goes through its own double detector, or double slit, along with a detector over here to determine which slits they went through. And here, you get two spots. Okay? All right, so imagine how wacky this must be. You've got one laser producing one beam of photons. If the photons went through the mirror, went straight through the mirror and went through double slits, you get the interference pattern. If they bounced off the mirror and went through the double slits with the detector, you get the two spots. Okay, so maybe it's the fact that it went through the mirror versus being bounced off. So what we can do is we can just flip this around. We can just move this detector over here, and then everything gets reversed. All right, so once you move the detector over here, then this one returns the 2 spots, and you get the interference pattern over here. So it has nothing to do with whether it went through the mirror or not, whether it bounced off the mirror or went through the mirror. It has to do with whether the detector is there. And then they've done some other experiments where they have like this, they have this detector over here, and they have this, have a mirror set up, and they got some other setup, got other mirrors going on. So basically, this beam of light takes many different routes through this experiment, and they've shown, and this is probably the wackiest result of all. They've shown that you can set up the beams so that they have different lengths, so that basically one beam is longer than the other beam. Therefore, it takes longer to traverse the longer beam than it does the shorter beam. And you can do something to the longer beam, and it'll influence the shorter beam. Okay, so basically, you can release a photon, and let's just say for our purposes, it takes 1 second to traverse the longer beam, and it takes only half a second to traverse the shorter beam. So you can do something to the longer beam. You can make it, you can affect the photon 1 second after it was released from the laser, and it'll have an effect on the photon that went through the shorter beam. In other words, somehow the photon on the longer beam can go back in time and tell the photon on the shorter beam that something was done to it. Now, if like the two-slit experiment wasn't mind-blowing enough, that is truly like totally crazy, right? That somehow these photons can become entangled so that something that happens to a photon in the future can affect something in the past. And they've shown this to be true, and it's correct, and it works this way. Any questions so far? I'm sure you have lots of questions, right? They're not necessarily questions I'm prepared to answer, or that physicists are prepared to answer, but any questions about what I've presented so far? Okay, so let's talk about qubits. So well, let me move this down here a bit. So a classical bit is either a 0 or a 1. It's never in between, it's never neither, it's never both, it's either a 0 or a 1. A qubit can be anywhere in between, right? It can be either a 0 or a 1, or it could be both or neither. It's not that it's both or neither, it's just that we don't know. We won't know whether it's a 0 or 1 until we actually measure it. So it's more convenient to represent a qubit not on a one-dimensional number line, but on a two-dimensional axis. So we've got this setup here, where essentially the x direction represents the probability that the qubit is in the 0 state, and the y direction represents the probability that it's in the 1 state. So if the qubit is in fact in the 0 state, it's at that point there on the axis. It's over there on the x direction, and it's not on the y direction. And if the qubit is very definitely a 1, it's up there, up in the y direction, but not in the x direction. And so the we use the unit circle to represent all the possible states that this qubit could be in, right? It could be here, it could be here, it could be down here, it could be over here, right? So the closer it is to the x-axis, the more likely it is to be a 0. The closer it is to the y-axis, the more likely it is to be a 1. And if it's right here in the middle, then it's got a 50-50 chance of either being a 0 or a 1. Okay, so we're using a unit circle. Unit circle means that the circle has a radius of 1. And if we basically plot out all the spots that are of distance 1 from the origin, we get this circle, and we call that the unit circle. So the coordinates of the qubit on the 0 state is 1, 0, if we use like the xy coordinates. It's 1, 0 for the 0 state. And for the 1 state, it's 0, 1, right? Those are just your Cartesian coordinates. What are the coordinates for the qubit if it's right halfway in between 0 and 1? And what's this one right here? Well, a little bit of trig involved here, or geometry. Right, we've got this triangle here. This is a 45-degree angle. This is a right triangle. We know that the hypotenuse is distance 1, because that's what it means for this to be the unit circle. What we want to know is, what is this distance and what is this distance?
So it's going to be root 2 over 2, root 2 over 2. What happens, how would we ever get a negative probability, though? How are we going to leave the first quadrant?
So there are other names for these other states. Right, so basically, this is where my understanding of quantum physics breaks down a little bit. It's convenient for us to represent this on a unit circle. It actually exists more in a three-dimensional thing called a block sphere, in which there's an x direction, a y direction, and a z direction. And those represent not, we're using the 2 dimensions to represent the probabilities, but what's actually going on is those represent the spin of the electron. The spin can be either clockwise or counterclockwise in the x direction, the y direction, and the z direction, okay? So the electron can be either spinning this way or this way. And then there's basically 3 orientations in 3-dimensional space for that electron to be in. So that's what's actually going on. So you're right. The probabilities can't really be negative, but this is a representation because it's a convenient mathematical representation for the actual spin of these things. Does that make sense? Okay?
Yes, thank you.
So they can spin in 3 different axes, and they can spin either clockwise or counterclockwise. And the interesting thing about these quantum particles is that they can switch their spin like instantaneously. They can be going clockwise one moment and then counterclockwise another moment. They don't like to go clockwise and then slow down and then stop and then reverse their direction, kind of like a motor would. They can be going one way and then suddenly go the other way. Or they can be spinning this way and then suddenly change their orientation to be going this way. They instantaneously flip between these orientations. And so what we're measuring is not like what their tilt is. We're representing their probability of being in one orientation or another. And we won't know what orientation they're actually in until we put a detector next to them and see what they are. Okay? So when we put the dot over here, we're not saying that the thing is tilted at 45 degrees. We're just saying that we don't know whether it's this way, we don't know whether it's spinning this way or this way, There's just a 50-50 chance that it is one or the other. Okay, so this point over here is 1 over root 2, comma 1 over root 2. I think you said something similar to that. So that's the Cartesian coordinates of this point that is halfway between 0 and 1. Okay, so for a classic bit, one of the fundamental operations for classic bits is not. If we apply the not operator to a 0, and think of it as being like a function, right? We're having a function called not. You pass in a 0, and you get back a 1. And if you pass in a 1, you get back a 0. In quantum terminology, if we take the x operation, which over here I said was the not equivalent in the quantum world, and we apply that to the 0 qubit, we should get back the 1 qubit. And if we apply that operation to the 1 qubit, we should get back the 0 qubit. Okay, that's the way we define the not operation as acting, that if you take a 0, you get back a 1, and if you take a 1, you get back a 0. That's what the not operation does. So mathematically, we can represent the not operation as a matrix. It looks like this, 0, 1, 1, 0, okay? And over here, we have the 0, 1, we got the 1, 0, and then we have the 1 over root 2's. So you can represent those as matrices as well. All I'm doing here is I'm just taking the horizontal representation and just making it vertical. So at this point, this is all just terminology, right? We're just making our definitions. We're just saying that if the xy coordinates are 1, 0, we can write it as a matrix by putting basically the x coordinate at the top and the y coordinate at the bottom. And then we define that to be the 0 qubit. And then if the coordinates are, let's see, did I get that right? Oops, I made a mistake right here. This is 0, 1, which means, oh boy, I messed this up. I was not paying attention. This is 1, 0, and this is 0, 1. There we go. Sorry about that. All right, so 1, 0, that's this point right here. We can represent it as 1, 0, so the x is on the top, y is on the bottom, and then that we define that to be the 0 qubit, and then 0, 1, we can write like this, and we define that to be the 1 qubit. The not operation, we write like this. So here's where your linear algebra comes into play. Now, you probably haven't taken a linear algebra class yet, so I'll just show you how to do this operation. So if you have A, B, C, D, X, Y. So if you have, remember, over here, oops, I'm applying the X operation to the 0 qubit. So X, if I say X is equal to this thing, and I say the 0 qubit is equal to this thing, oops, this thing here, I can basically say that x of 0 can be written as 0, 1. No, I'll do it like this. 0, 1, 1, 0, 1, 0. Okay, so here all I did was I just said, if I say x is this thing, then I'm going to put that there. And if I say the 0 qubit is this thing, then I'm going to put that there. I just put them right next to each other. Okay, so if you have a 2 by 2 matrix multiplied by a 1 by 2 matrix, what you get is a 1 by 2 matrix. So you have two values, one at the top and one at the bottom. And the way you calculate it is it's AX plus BY on the top, and it's CX plus DY on the bottom. Okay, so you multiply these two together, and that becomes this term. And then you multiply these two together, and it becomes this term, and you add them together, and you get your top number. And then you multiply these two together, whoops, not those, these two together, and it becomes this term. And then you multiply these together, and it becomes this term, and then you add them together to get your bottom number. Right? So this is ultimately, so a little bit of background here. All this stuff was figured out decades ago. Decades ago, scientists realized that they could make quantum computers, and they started defining these operations. They said, this is the way we want the computer to behave. We want to define a NOT operation, and this is the way it's going to work. Just like in a classical computer, we have a NOT operation, and this is the way it works. You put in a 0, you get a 1. You get a 1, you put a 0. And then, once they defined what it was supposed to do, then they went about building that circuit to make it work. It's done with a couple transistors and a couple resistors, right? You can actually build that physical electronic circuit to make the computer do the NOT operation. So for quantum computers, they figured out, here are the mathematical things that we want the quantum computer to do. Like a classical computer can do ands and nots and ors and exclusive ors. You know, those are all the fundamental operations it can do. Classical computer can do this NOT. It can do a bunch of other operations to maybe change the spin of an electron. So there's different names for those operations. So this is what we want the quantum computer to do. And it wasn't until just in the past few years that they were actually able to build a quantum computer. And they said, here's this mathematical model for how it's supposed to work. Now we're going to build a computer to behave like that. So I think that was one of the challenging things for me to get my head around, was that we are not designing these operations because that's the way the real world works. I mean, it so happens that it does. We're not trying to model the way quantum particles work. What we're trying to do is impose a mathematical model on top of it to say, like, here's all these things that have spin and energy states, and here are these mathematical operations, these computational operations we want to apply to those things. Let's build a computer that does that. Okay, so what I'm going over here is, here's what we want the NOT operation to do. If we pass in a 0 qubit, we should get a 1 qubit out. Let's build a computer that does that. If we pass in an electron that's in the 0 state, and we pass it through this weird quantum thing, out comes an electron in the 1 state. If we pass an electron in the 1 state, and it goes through this weird thing, out pops an electron in the 0 state. So we've made a quantum computer that does what we want it to do. So I'm going through all this matrix stuff right now because this is the mathematical model that the computational physicists set up. And then IBM and other companies went about building a computer that actually behaves like this. Okay, so we do the NOT operation. So we'll go, whoops, x on the 0 state is going to be 0, 1, 1, 0, 1, 0, right? So this is the x, and this is the 0 state. And then we're going to do this multiplication. So we get 0 times 1 plus 1 times 0, right? That's ax plus by. 0 times 1 plus 1 times 0. Let me draw it like this, right? 0 times 1 plus 1 times 0. And then for the bottom number over here, we've got 1 times 1 plus 0 times 0. So it's these two numbers. 1 times 1 plus 0 times 0. Okay, and then we get 0 plus 0, and we get 1 plus 0. That's right, that's this, and this, and this, and this. And that gives us 0 and 1, which is exactly what we wanted. We passed in a 1, 0, and we got a 0, 1 out. So that's what the NOT operation does. On the unit circle, it takes something that's over at the X spot and flips it up to the Y spot, right? Rotates it on the circle. You're probably going, this is boring, right? But this, so I guess I should say, quantum computing is now here in the year 2021, where classical computing was back in the 1940s. Just starting out. Back in the 1940s, the computers were huge, they were hot, they consumed lots of power, they were unreliable, they were slow, and you had to program them by taking these computational units and kind of like physically hooking them up to each other, or feeding punch cards or punch tape to them. And that's where quantum computing is right now, is we've got these huge, large machines. They run hot. Actually, they're very cold inside, but they have to have all these cooling units that run hot to pull all the heat out of them. And they're slow, and they don't have very much memory. And you have to program them by doing these, almost like programming them in an assembly language, right? You're doing these NOT operations and these Hadamard operations, and you hook them all together, and you can do very simple computations. That's where we are right now. So, maybe if when you go on to upper division or graduate work and you take a course in quantum computing, a real course in quantum computing, you'll spend a week or two going through all of this math stuff to show that it all works, that it's all consistent with each other. And they say, okay, now that we've shown that it all works and all consistent, we won't do the math again. We'll just work on knowing that we can do X means not, and H means Hadamard, and we know that the computer behaves that way. So let's do this. Here we got 0 times 1 plus 0 times 0. Someone was saying something.
Your 1 and 0 is flipped in your first, the second matrix there. There you go.
Thank you. Yeah, my eyes go buggy after looking at all these zeros and ones after a while. All right, 0 times 0 plus 1 times 1. And then 1 times 0 plus 0 times 1. And we get 0 plus 1, and we get 0 plus 0. And that gives us 1, 0, which is exactly what we wanted. We take in the 1, and we get out a 0. Okay, so on that unit circle, we have these two spots. This is the 1 state. This is the 0 state. And then we had this third one, which was halfway in between. And we represent that matrix-wise as 1 over root 2 and 1 over root 2. But there's a name for that spot, and we will call that the plus state. And there's a corresponding minus state as well. I think it's down here. Okay, so the Hadamard operation, basically what it does is it takes a quantum bit and it puts it into a superposition where you don't know whether it's a 1 or a 0. So it takes a 0 and it puts it into the plus state. And it takes a 1 and it also puts into a state where you can't tell whether it's a 1 or 0. But let's try that out. So this is the H operation, and if we take H of the 0, we should get the plus state. Okay, so we should be able to take something over here and move it into superposition. Now, the H operation can be represented as the matrix 1 over root 2 of 1, 1, 1, negative 1, which is the same thing as 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. Right? All you do is you just distribute this root 2 amongst all the cells in the matrix. Okay, so if we take Hadamard of 0, it's 1 over root 2, 1 over root 2, 1 over root 2. When you do quantum computing, you write 1 over root 2 a lot. And remember, the 0 qubit can be represented with 1, 0. All right, so we just multiply this out. 1 over root 2 times 1 plus 1 over root 2 times 0. That's our top. And then 1 over root 2 times 1 plus negative 1 over root 2 times 0. Okay, so this is 1 over root 2 plus 0, and the bottom is 1 over root 2 plus 0 as well. And that gives us 1 over root 2, 1 over root 2, which is exactly what we wanted. Right? That's the spot right here. Okay, so if you put in a 0 qubit, you get the plus. Now, let's see what happens if we put in the plus and we apply the Hadamard operation to that. Oh man, in all my confusion getting set up today, I forgot to hit record on Zoom, which is crazy, right? Because I had that that TED Talk on there. So what I'll have to do is I'll have to just post a link to the YouTube video, and then I'll have to tell you what other video we watched in the middle before YouTube itself cut that off. All right, so I'll figure that out. Okay, all right, so what do you think is going to happen if we pass the plus qubit in to the Hadamard operator? Okay, so this is the same Hadamard matrix that we had up here, and then this is the plus, which is this one over here. All right, here we go. 1 over root 2 times 1 over root 2, so that's this times this, plus 1 over root 2 times 1 over root 2, that's this times this, all over 1 over root 2 times 1 over root 2, that's this times this, and then plus, or I could say minus, right, because I know it's a negative, minus 1 over root 2 times 1 over root 2. That's this one here. Okay, 1 over root 2 squared is just a half. So we get a half plus a half. And we get, on the bottom, we get a half minus a half. And that gives us, oh my goodness, a 1 over a 0. All right, so if you take the 0 qubit and you apply the Hadamard operator, it rotates it over to the plus. And if you take the plus and you apply the Hadamard operator, it rotates it back down to the 0. Crazy, huh? Okay, so now we know about this plus position. We got 2 more calculations to quickly do, and then we can do that coin game that was showed in the video. What happens if we do x on plus? Okay, so x is 0, 1, 1, 0, and plus is 1 over root 2, 1 over root 2. Sorry, it gets sloppy after a while, but hopefully you can read that. So you got 0 times 1 over root 2 plus 1 times 1 over root 2. And then on the bottom, you got 1 times 1 over root 2 plus 0 times 1 over root 2. And you get 0 plus 1 over root 2 over 1 over root 2 plus 0, which gives us 1 over root 2, 1 over root 2. Okay, whoa, that's crazy there. So if you take a qubit that is in the superposition state and you apply the NOT operator to it, it stays in superposition. So we can now draw this state diagram. Right? We've got these 3 states. We've got the 0 state, we've got the 1 state, and we have the plus state. So if we start in the 0 state and we apply the Hadamard operator, we go to the plus state. And if we're in the plus state and we apply the Hadamard operator, we go back to the 0 state. If we're in the plus state and we apply the X operator, it goes back to itself. And if we apply the X to the 0 state, we go to the 1 state. And if we apply the X to the 1 state, we go back to the 0 state. So we've got this state diagram that we can follow. And this allows us to basically chain up all these operators and see what happens. All right, so we ran all these calculations, and now we've got the state diagram. So once we've got this state diagram, we can essentially dispense with all those calculations. We know that they work. We know that they work. We've got the state diagram. Now we can do the coin flip game. And if you remember, the coin flip game was we started from heads, and then, oh, I should say, let's say heads equals the 0 state. Tails is the 1 state. And if you remember that game, we start with the 0, which means start with heads, put it into superposition using the H operation, and then you can either do the X operation, which means you flip it one more time, or you can not do it. So you could elect to do the X operation, and then the computer does its thing again, which is to apply the Hadamard operator again. And what do we get? And the other possibility was we start with the 0, we do the Hadamard operation, and then we elect not to flip it one more time. So the computer then does its thing, and what do we get? Okay, so we have this state diagram. Right? We don't have to run all the math because we already did it. Actually, let me do it like this. I'm just going to use like lighter colors. Okay, so we have our 0 here. We've got our 1, and we have our plus. And we know that if we do X on the plus, we go back to ourselves. If we do H on the 0, we go to plus. If we do H on the plus, we go back to 0. If we do X on the 0, we go to 1. And if we do X on the 1, we go to 0. Okay, so there's our state diagram. Okay, so we start at 0. And then we do H, which means we start here and we go this way. And then we do an X, and then we do an H. And we end up back at 0. Which means we end up back at heads. And then if we start at heads, do the H and do the H again. We do the H and then do the H again. Then we also end up at heads. And that's how the computer was able to win every single time. So it's almost like you have this can of paint, right? And on one side of the can of paint, you've got, let's say, green paint. And on the other side, you've got red paint. And, it's very distinctly not mixed up. But then you insert your stirring stick, and the H operation is like you stir that whole thing up, right? So all that paint mixes together. And you can elect to either continue mixing it one more time or not mix it. And then the computer does this H operation again. And this Hadamard operation works really cool because you can take that mixed up paint and you can unmix it back to the 0 state. So it starts in the 0 state, you mix it up, and then you can unmix it back to 0. So once that paint is all mixed up, it doesn't matter how much more you continue to mix it. You can then unmix it back to 0, which is something you really can't do in real life. So like I said earlier, this two-dimensional axis is not really like how real quantum particles work. It's a mathematical model for quantum computation. So in a classical computer, you either got a 0 or a 1, and you can represent that on a one-dimensional number line. It's 0 or 1, but not both and not neither. In quantum computing, it can be a 0 or a 1, anything in between, and there's also some additional things that can be outside of that, right? So it's really on a continuous line, and because of that, it's more convenient to represent it on a two-dimensional axis. Really, it's a three-dimensional sphere. So there are even some additional states involved. But for quantum computing, two-dimensional one is good enough for us. You can, if you take a course in quantum computing, extend it out to the third dimension, and then you'll find there's an x operation, which basically rotates it, on the x. There's really the x-axis really is like pointing outward. So it rotates around the x-axis. There's a y operation that rotates around the y-axis, and there's a z operation that rotates around the z-axis. But they all do the same thing. They rotate at 90 degrees in one of those directions. And so with combinations of those operations, you can get this quantum bit to flip to all, 8 different orientations. And then if you do a quantum bit and you rotate it like this, let's say it's rotating, let's say the quantum bit is like faced up, right? You rotate it this way, now it's faced like to the left or to the right or whatever that is. And then if you rotate it around this way, it's still facing to the left, and then you can rotate it this way, but then you can get it like all twisted around so that if you apply some of these operations, it's now flipped, now it's faced maybe in its original direction, but now it's faced down instead of up, right? So you can do these operations, and you can get that quantum bit to not only change its direction, but change its spin as well. So you sort of have to picturing things in 3 dimensions rather than just 2 dimensions, or 1 dimension like it is in classical computing. Okay, so that's my quick introduction to the fundamental operations of quantum computing. Where you can go from here is, now that you have the fundamental operations, and there's more than that. There's one called the C-naught operation. That is called a conditional knot, and it works on 2 qubits. And the way that one works is if the first qubit is a 0, it leaves the second bit the same. And if the first qubit is a 1, it flips the other one to the opposite state. So it's a knot operation, but conditional on another qubit. And this represents the entanglement between 2 quantum bits. You can take one quantum bit, and cause it to affect the state of another quantum bit. So again, quantum entanglement is a real phenomenon that physicists have proved is possible to do, and then we've just defined a computational operation that takes advantage of that. So in that video, she alluded to things like quantum teleportation. And this is something that researchers have actually done. What they've done is they've taken 2 quantum bits and they entangled them so that what you do to one affects the other one. Albert Einstein called this spooky action at a distance, right? Because these 2 quantum bits are no longer touching each other, and what you do to one, you can flip one of them and it will cause the other one to flip. And so what they did was they took these 2 quantum bits that are now entangled together, they put one of them onto a rocket and sent it into space. They left the other one here on Earth. And so the other quantum qubit is now orbiting, the Earth, and we got this one down here, and you change this one, and the other one changes. So they're now separated by, hundreds of miles, and what you do to one affects the other. What does that mean? That means that we show that we can basically transfer information across vast distances without actually physically sending a signal from one to the other. Right? It's not like we're using radios where we're sending a radio signal from a base station out to a satellite. We are transporting an entangled bit out into space, and then without sending a signal from one to the other, we can cause one quantum bit to change the state of the other one. I mean, that has like huge implications for talking to satellites that are way out there in the solar system, right? So rather than having these big giant radio dishes that are sending powerful signals all the way across the vastness of space, all we have to do is send some qubits along with them, and then we can send information from Earth to the satellite just by changing one of them down here, and it causes the other one to change over there. And the satellite can communicate back with us the same way. It changes its qubit, and ours changes. So they can basically send ones and zeros back across vast distances without consuming the energy of sending radio signals. Now, of course, the next question is, how long does it take? So it turns out you still got speed of light measurements in here. So you're not instantaneously sending information from one place to the other. It still takes the speed of light time to get the information across. We're not sure why exactly, but nevertheless, the speed of light is still that speed limit of the transfer of information across. We're not physically sending anything between the two, but it still takes speed of light time to move that information across. So unfortunately, we haven't solved that problem of being able to communicate across vast distances instantaneously like they do in Star Trek. But being able to do it without physically sending energy from one particle to the other is probably a big thing. So those particles are still connected somehow? Yeah, it's called quantum entanglement. They can get two quantum particles to coexist. And one of the ways to do it is with that half mirror. There's special kinds of mirrors. They're not the cheap half mirrors you can get like at the hardware store. They're special mirrors. They're kind of expensive. You can get them on eBay, actually. And you can send photons through these things, and out will come two beams of photons, but the two of them now are entangled. They are now identical to each other. They're going in different directions, but everything about the so basically one photon goes in and two photons come out, and the two photons are now clones of each other. Same spin, same everything about them, and so they're now entangled. And then you can now do one thing to one photon and it will affect the other one. So you can actually, you can go and buy one of these mirrors and you can show that, I mean, it's kind of an elaborate experiment, but you can do this yourself. It costs a couple $100 to do, but you can do this experiment where you can basically take a beam of photons, pass it through one of these mirrors, and then you can change the polarization of one of the beams, and it will change the polarization of the other one. Oh gosh, what's the name of the mirror? I don't remember. Let me see if I can remember. I think I ended up adding one to my eBay cart at one point. Thinking I'm going to buy one of these things, but they're really expensive. No, I don't have it anymore. No. Now you got me all curious. What is this thing called? Yeah, I can't offhand find the name of it. It's not a mirror made out of glass like a regular mirror. It's made out of a quartz crystal. And this particular crystal has this property where you can pass photons through it and it will clone them, basically. Or maybe I've got that slightly wrong. It doesn't take one photon and turn it into two. That would be almost like creating matter out of nothing. It could take two photons and make one of them match the other one. So two go in, two go out, but they started out being different and then they come out being the same. So once you have that, now you can do things like quantum algorithms. And like I said, quantum computing is still now in its infancy. And so the algorithms they can do are pretty simple, but they've shown that you can do things like factor a number into its prime factors faster than you can do it on a regular computer. On a regular computer, in order to find the two prime factors of a composite number, you have to like run some loops, right? You have to try every possible factor until you find the one that works. On a quantum computer, you can do it faster than brute force. It's not instantaneous, it's still got some loops to run, but you can do it faster than brute force. Another quantum algorithm that you can do is the minimum maximum one, right? So imagine you've got a room full of people, and you say you want to find the person who is like, you know, the oldest person or the youngest person or something like that. And so what you have to do is you have to query each person in the room. What's your age? What's your age? What's your age? What's your age? And you'll have to query every single person in the room in order to figure out who's the oldest person. So if you have 100 people in the room, you'll have to query 100 people before you figure out who's the oldest person. On a quantum computer, if you have 100 qubits and you want to find out which one of them represents the oldest person in the room. So you have 100 people in the room, you assign each one of them a qubit. So you got 100 qubits. And then you want to ask the question, which of those qubits represents the oldest person in the room? You'll only have to run the loop 10 times. Okay? So in a classical algorithm, you'll have to run the loop 100 times. You'll have to query every 100 people and find out which one's the oldest person. In a quantum computer, you only have to run the loop 10 times. It's the square root of 100. And the way it kind of works, and this is just a really like analog to the real world, is you announce to the group of people, the person who is the oldest, please stand up. Okay? So simultaneously, 100 people got that instruction to stand up if they're the oldest person. And so they all kind of like look confused at first, and they kind of look around, and then a few of them stand up, thinking they're the oldest people. And then you say like, okay, of the people who are still standing, if you are the oldest person, please stand up. And so they kind of like look at each other again, and a few of them sit down, and a few of them are still standing. And then you announce it again. If you're the oldest person, stand up. And so a few more sit down, and so you do that a few more times, and then eventually you get to the point where only one person is standing. Okay, that's crazy, but that's the way that algorithm works. And you only have to do that, hi. You only have to do that 10 times. So you just announce to all 100 people, please stand up if you're the oldest person, and after 10 iterations of that, the oldest person will be standing up, guaranteed. It's crazy, but it works. And the way you do things like you're factoring numbers is, let's say you're trying to factor the number, oh, I don't know, 15, right? And so you got 15 qubits, and each one of those qubits represents whether or not that number is a factor of 15. And so we know that 3 and 5 are factors of 15. So qubit number 3 and qubit number 5 are factors. And so what you basically do is you announce to all those qubits, if you are a factor of 15, please stand up. If you are not a factor of 15, please sit down. In other words, if you are a factor of 15, move yourself into the 1 state. And if you are not a factor of 15, move yourself into the 0 state. And so you start them all out in that plus state, right? They're all in superposition. They could be either a factor or they could not be a factor. You start them all out in that state, and then you run them through this box. And this box is the complex part. But basically, each one of the bits runs through those boxes. And at the end of one iteration, a few of them will have moved themselves into the 1 state, and a few of them will have moved themselves into the 0 state. And then you do that again. And a few of those will have moved themselves back into the 0 state, and a few of them will still be in the 1 state. And so after the square root of 15, what is that? Ish, right? About 4, somewhere between 4 and 5 iterations, you will have the factors of 15. The 3 qubit and the 5 qubit will be in the 1 state, and all the others will be in the 0 state. Crazy. But so this factoring algorithm is not instantaneous. So quantum computers will not factor numbers instantaneously or even after 1 iteration, but they can do it in the square root of the number you're trying to factor, I think. I think that's what the running time is, which is a whole lot faster than brute force. And so what's the implications of that? Well, it means that things like RSA can be broken quickly by quantum computers using an algorithm called Shor's algorithm. That's basically what I described there, Shor's algorithm. So if quantum computers can break RSA quickly, what does that mean about protecting our transactions right now? Well, it means currently we don't have quantum computers that are big enough to be able to factor the large 200-digit numbers that we currently have. But, you know, give it a few decades and we'll probably be there. But it does mean that we have to start thinking about what kinds of encryption algorithms can we develop or develop now that when quantum computers have finally caught up, we can implement right away to be able to protect our transactions that even quantum computers can't break. So an algorithm so complex that even a quantum computer can't break that computation faster than brute force. And brute force for a quantum computer may be using, let's say, you know, if we're talking about a 2,000-bit number, well, now you need 2 to the 2,000th qubits to be able to do that. Well, you know, constructing such a computer is, you know, all we can do right now is basically build computers that have about 20 qubits in it. How could we possibly build a computer that has 2 to the 2,000th qubits, given that the number of atoms in the universe is like 2 to the 200th? Right? You need a quantum computer that had more qubits than the number of atoms in the universe. All right? Can we construct such a thing? I don't know, but maybe using the power of quantum computers, we can somehow compress that into fewer qubits. I don't know. That would be something for people like you who are just starting out in their computing careers to start studying. So I would say it's a good idea now, in the year 2021 or 2022, to start getting the fundamentals of quantum computing so that when it becomes more practical, you're ready to go. You can be on the cutting edge of quantum computing research when we've got computers that are finally practical and easily obtainable. I mean, you can go on right now and you can use IBM's computers. They've only got a few qubits. You can only get access to like 5 or 6 qubits at a time. And it takes a long time to run your program, because not only because the computers are slow, but also because there are hundreds of other people running their programs. And so you have to queue up to run your program. It can take several hours for your program to actually get onto the computer itself. That's why we have simulators. You can download free simulators and run your programs there. You know, so I would say get started now. There's plenty of online courses you can take that give you the fundamentals of quantum computing. There are courses you can take at some of the leading universities for free, and you can start investigating that. But if you are not ready to start that, I would say at the very least, take an introduction to quantum physics. You know, learn about atoms and quantum effects. You know, maybe you don't have to take a graduate level one, but you ought to know about the basics of things like superposition and energy states. You know, it's kind of like if you wanted to be a computer programmer back in the 1940s, you needed an electrical engineering degree to understand how all the transistors and the vacuum tubes and the wires worked. These days, you don't need that, right? You can just program a computer, you can sit down and program it in Python or C or Java or whatever. We're not at that point yet. We're still at the point where you need to know the fundamental operations, the knots, the C knots, the Hadamards, the X and the Y operations, and the Z operations to be able to program a quantum computer. Kind of like you need to know assembly language to be able to program those computers back in the 1940s. So we're kind of like programming quantum computers using quantum assembly language, if you will. In 10, 15 years or so, we'll get to the point where we can just use, you know, programming languages that look more like traditional ones. We're not at that point yet. So maybe take a course in quantum physics, introductory course, right? Just to get the basics. Take your linear algebra class and pay attention to the matrix manipulation, the matrix algebra. As you saw today, really important to be able to do the matrix calculations. Then you'll be in a really good position to be able to take a course in quantum computing. Pay attention to your calculus class too. I took, in my quantum computing course, there was a little bit of calculus involved, just a little bit. Not too much. pay attention to limits and integrals and derivatives. Again, I expect within 10 years, we'll get to the point where you don't need to know that stuff. But right now, you do. There's a question here. Is there no need for binary search in a quantum computer? That's correct. You don't. Let's see. Is square root of n is faster than log n, isn't it? I think it might be. Yeah. Or at least, the thing about binary search is you can do it in log n time, but the prerequisite is that the elements already need to be sorted. So although you can do the binary search in log n time, you have to do the sort, which is n log n time. And that's definitely faster, or definitely slower than square root of n time. So this allows you to search through an array and not have to sort it first. That algorithm I was describing about people standing up. You don't have to sort it first. If you want to find out who's the older person in the room, but you sort all the people by their age first, then it's easy, right? It's just the person at the end of the array. What else we got here? 0 is both 0 and 1. And or both or not. -1 is both 0 and 1. Or oh, is there binary involved? Well, sort of. Current thought is that quantum computers and classical computers will work together. That you need a classical computer to be able to measure the results of a quantum computer currently. Kind of like you can't run a video game on a GPU alone. You still need a regular computer to power the GPU, to tell the GPU what to do. So same thing with a quantum computer. Think of a quantum computer computing like a GPU, right? It's this add-on that you have hooked to a regular computer. You use a regular computer to basically tell the quantum computer what to do and to measure its results. So yeah, there's still binary involved because the results you're going to get out of a quantum computer are ones and zeros. While the algorithm is running in the computer, then there can be this superposition where it's either neither a 0 or a 1, or it's both, or it's neither. But once the results come back out, they're just zeros and ones. So you're taking advantage of the fact that you can do this superposition and entanglement while the program is running in the quantum computer. Anything else? So I think on Thursday, probably Thursday, I will get a chance to implement these matrix operations that you saw in a C program. I'm planning on doing it maybe on Thursday. So we'll write a program that represents these quantum bits as a C structure, and then we'll apply these operations to it, and we'll basically have built a quantum computer simulator using a standard programming language. Okay, so I think that's all the time we got for today.
All right. Thank you,
All right.
Professor.
Yeah, so there's people in my class, just remember that within the next day or so, you're going to have two things appear. You're going to have a end of semester kind of assessment where you just go through and kind of summarize everything you did through the semester, and then also make an appointment for meeting with me next week during finals week for about 5 minutes or so, just to go over that assessment and figure out, ultimately we'll come to an agreement about what your grade in the course is going to be. Can I elaborate on the simulators I mentioned? So there's a Python library called QIS-Kit, and that allows you to simulate a quantum computer using the Python programming language. So you define your ones and zeros, but you define them as qubits, and then you can do these operations. There's a Hadamard operation, the NOT operation, the XYZ operations, plus the dozen or so other operations. And you can simulate a quantum computer. And you can actually program in things like Shor's algorithm and the algorithm for searching through an array. You know, you can do it yourself. For anyone who's still working on the lab due on the 1st, just remember that there still are tutors and there still are assistants. So if you go onto the Canvas site, scroll down a little bit to where it says Zoom links, and then there's a link to the assistant's calendar. You can follow that and get a calendar when they're available. Okay, folks, let's wrap it up. Have a good day. I'll see some of you tomorrow. See the rest of you on Wednesday.
Great. Thanks again, Professor.
right.
Take care.
You too.
Thank you.
Bye-bye. All right, and unfortunately, the YouTube stream is the only one in which I remember to hit record. And then it has that blank section where I was showing the TED video. So I guess what I'll have to do is in the description, I'll have to link to what that TED video was. So you can go and watch that separately. Okay. Well, have a good day, everyone. And again, like I'll see some of you on Wednesday. I'll see some of you tomorrow. Have a good day. Take care. Bye-bye.